Okay, we'll get back to trig substitution here. This is section 7.3. Here's another example. I've got a definite integral, and when you integrate the function, the square root of x squared minus 3 divided by x, going from root 3 to 2. Root 3 is less than 2, so the bounds don't need to be flipped, right? Okay, so there's three types of substitutions here, and it looks like this integral is going to involve the square root of u squared minus a squared. A is a number, right? So a would be the square root of 3, because the square root of 3 squared is 3. So x would be equal to root 3 times secant theta, okay? If secant theta is equal to x divided by root 3, let's see, secant theta is the reciprocal of cosine theta, and cosine theta is adjacent over hypotenuse, so secant theta would be the hypotenuse over the adjacent side. So x is the hypotenuse, and root 3 would be the adjacent side. The leftover leg of the triangle, then the opposite side, would be the expression that led us to the trig substitution to begin with. Okay, dx then is root 3 times secant theta times tangent theta d theta. Okay, and then the square root of x squared minus 3 is, x is root 3 secant theta. So if I square that, I'll get 3 secant squared theta. Okay, and then minus 3, that's all underneath the radical. If I factor out 3, then secant squared theta minus 1, that's by definition tangent squared theta. Okay, so I got the square root of 3 times tangent squared theta, okay, which is going to give me root 3 times tangent theta. Remember that you don't need to worry about absolute value bars for anything that we're doing here, okay, because of the conditions on theta. So, and we always need these three items to make our substitution, okay? Now, this is a definite integral, so I'll also need to switch the bounds. If I don't switch the bounds, then I'm mixing x and theta, and that's bad. That will give me a wrong answer, okay? So if x is 2, let's see, I got 2 equals root 3 secant theta. Well, secant theta would be 2 divided by root 3, okay? So secant theta, that's 1 divided by cosine theta. Cosine theta is root 3 divided by 2. So for what value of theta is cosine theta equal to root 3 over 2? Well, cosine of pi over 6 gives me root 3 divided by 2. So the upper bound is going to be pi over 6. The lower bound, let's see, when x is root 3, I got root 3 equals root 3 times secant theta. Divide both sides by root 3, and so secant theta would be 1. Secant theta, again, is the reciprocal of cosine theta, so 1 divided by cosine theta equals 1, or multiply both sides by cosine theta. Cosine theta equals 1. So when does cosine theta equal 1? Or for what value of theta? Theta would have to be 0, right? Because cosine of 0 gives me 1. Okay, so my new integral then is we're going to be going from 0 to pi over 6. The square root of x squared minus 3 is root 3 times tangent theta. The dx part, that's root 3 times secant theta times tangent theta d theta. Okay, and then x is root 3 times secant theta. Okay, so my new integral here is all involving theta. These root 3's will cancel. Here's a root 3. You can bring that outside the new integral. Secant thetas will cancel. Okay, so you're going to have root 3 times the integral going from 0 to pi over 6 of tangent squared theta d theta. Okay, well, tangent squared theta is secant squared theta minus 1. Okay, so that allows me to then get the antiderivative. The antiderivative of secant squared theta is tangent theta. The antiderivative of 1 is theta. And I'm going from 0 to pi over 6. So then I'll plug in the bounds. Now, by the way, whenever I have a definite integral, so I'm substituting back for x. I'm not doing that when I have a definite integral. Okay, so whenever I have bounds here, you're going to keep everything in terms of theta and then plug in the bounds, and then you got your answer. Okay, so let's see. I plug in the upper bound first, lower bound second. So tangent of pi over 6 is 1 over root 3, opposite over adjacent, minus theta is pi over 6. Okay, and then minus, when I plug in 0, tangent of 0 is 0, and then minus 0, so I'll be subtracting 0 there. And I guess the last thing I did was distribute the root 3 into these two terms. So 1 minus root 3 times pi over 6, that'd be the exact answer. And again, always keep the answers in exact form, right? There's no reason to go to the calculator for any of this stuff here. Okay, so again, the point of that one is to say that sometimes we have definite integrals, okay? Make sure that your notation looks good, you're writing the bounds, and when you make the trig substitution for theta, x is not coming back, okay? Now here's another example. I got the integral for x divided by the square root of x squared plus 4, okay? So I see, if I wanted to, I could use a trig substitution, okay? But I don't want to do that though, because I can use just a simple u substitution here. You see, if I let u be x squared plus 4, du is 2x dx, and so I'll have a 1/2 coming outside the new integral involving u. 1/2 du would be what I'm going to write there for the numerator. So I got 1/2 times the integral for du is up top, divided by the square root of u. Okay, 1 over the square root of u is u to the negative 1/2 power. And when I find the antiderivative, I've got u to the 1/2 divided by 1/2. The 1/2s will cancel. So I got u to the 1/2, or the square root of u, plus a constant. Replace u. U is x squared plus 4, so my answer would be the square root of x squared plus 4, plus c. Now there's a note here, which is really important. It says you can use the substitution x equals 2 times tangent theta, right? Because we've got the square root of x squared plus 4. Could like we could, if we wanted to, make a trig substitution. That would be fine, but we're creating more work for ourselves. Okay, so the fact is that when a trig substitution is possible, it might not be the best method. So you want to look for a simpler method first, right? So this would be the easiest way to do this problem, is just a regular u substitution. Okay. Now, all the other examples that I showed you, all three of them, you couldn't use a u substitution no matter what you did for u, okay? Let's see. Now, this next example, actually, why don't we go ahead and stop the video right here, and I'll do these last two examples in the next video, okay?